In today's lesson, we're going to be writing polynomial functions and models. In our first example here, we're going to write the cubic function whose graph is shown. And to write the function of this, we're going to start off by writing it in factored form as opposed to using standard form. And what strikes me is that we know what each of the zeros or x-intercepts are going to be, and that's why writing it in factored form is going to be so much easier. So I'll start off and write y equals a, and then with our first point at -2, 0, so the root is x equals -2, so therefore the factor is going to be x plus 2. The next root is -1, 0, so our next factor is going to be x plus 1. And then finally we have 1, 0, so our next factor is going to be x minus 1. Now, all I need here is to figure out what the a value is. And that's when the 0, 6 comes in handy. I'm going to substitute that point in and use that to determine what my a value is. So y is 6, and we're trying to solve for a, and x values are all 0. So 0 plus 2 times 0 plus 1 times 0 minus 1. When I simplify that, it's going to be a, and then it's going to be 2 times 1 times -1, which simply simplifies to -2a. Now all I have to do is divide both sides by -2, and I finally have my a value, which is -3. So finally, we can get our equation as y equals -3, and then x plus 2, x plus 1, and then x minus 1. And since it doesn't specify which form to use it in, or we need to put it in, we can leave it like this. However, if I did want to put it in standard form, I would just multiply all these factors together. But this will be good enough for our purposes. In our next example, we're going to use a thing called finite differences to find a polynomial function that fits the data in this table. So basically, the gist of the question is, we are given a table and we need to find the equation that will fit that data. A polynomial function is all we know. We don't even know the degree. So we're not given a whole lot to work with. So what we're going to do is we're going to use a thing called finite differences to help us figure out what the degree of the polynomial is. And the way it works is I'm going to get a set of numbers. 6 is usually a good amount. And so I'm going to use f of 1, f of 2, I'm just going to write these down, f of 3, f of 4, f of 5, and f of 6. And right below there, I'm going to write down the value of each of these. So f of 1 is 6, f of 2 is 15, f of 3 is 22, f of 4 is 21, f of 5 is 6, and f of 6 is -29. And what I'm going to do is I'm going to go and subtract each of these from left to right. But we have to be careful how we do this. So what I'm doing is I'm just going to be subtracting these like so. So I'm going to subtract the 6 with the 15, but I'm going to say 15 minus 6. Okay, and so that's going to give me 9. So I'll say, well, that's which equals, well, 9. And then I'm going to just kind of do this through the whole thing, just from left to right. So then I'm going to say, well, 22 minus 15, oh, well, that equals, and let me get a different color here, that's going to give me 7. So I'm going to write down 7. And then 22 and 21. So well, I'm going to say 21 minus 22. Well, that equals, and specifically -1. So we do want to include the signs. And then 21 and 6. So 6 minus 21, running out of space here, which is going to give me -15. And finally, -29 minus 6. And that equals -35. Okay, so these numbers here, the 9, the 7, the -1, the -15, and the -35, these are called our first order differences. And what the first order differences tell us is that, well, this would tell us the degree of the polynomial that we're going to be using. However, what I'm looking for specifically is for these numbers to repeat. So since I do not have any of these numbers repeating, and all of them have to repeat, this is not going to be a first degree polynomial. If they did repeat on this line, then it would be a polynomial of the first degree. Just think about finding the differences of a line. You find the differences of those numbers are all the same. So I'm going to go on to the next level and subtract and see if the numbers repeat there. So I'll continue. So now I'm going to take 7 minus 9, that's going to give me -2, and then -1 minus 7 is -8, -15 minus -1, or +1 in this case, would be 14, and then -35 minus -15, which is going to be +15, is -20. And these numbers here are our second order differences. But again, the numbers do not repeat, so our polynomial is not of degree 2. So the order corresponds to the degree. So I will go another level, all inception style. So now -8 and 2, that's going to give me -6, -14 and minus -8 or +8 gives me -6, and -20 minus -14 also gives me -6. And look what we have going on here. Notice that all of the numbers repeat. They're all repeats at -6. And this is going to be our third order differences. And because they repeated our third order differences, that means that our function is going to have a degree of 3, or it's going to be cubic. So now I know what type of polynomial we're dealing with. It's going to be a cubic function, and the standard form of a cubic function can be written as ax cubed plus bx squared plus cx plus d, and then equals our constant, which I'll call y. And so that's the standard form. Now what we're going to do is we're going to go ahead and grab some of these values here. I'm just going to grab the first 4 x's and the first 4 f of x's, or in this case I'll use them as y's, and I'm going to plug them in and then solve for a, b, c, and d, what would be the coefficients of our equation in standard form. Okay, so and we've done this before with quadratic, so it's the same process, just a larger degree. You can refer to section 4.10 in standard form for reference of how we did that with the quadratics. So anyway, we're trying to solve for a, b, c, and d in order to come up with our equation. So I'm going to start substituting these in. So the first point was 1 and 6. So it's going to be a, and then it's going to be 1 cubed plus b times 1 squared plus c times 1 plus d equals the constant of 6. The next equation, a is, so x is 2, so 2 cubed plus b times 2 squared plus c times 2 plus d equals, and then the y was 15 if we refer to our table. And then we're going to need, so basically I'm going to need 4 equations here, and the reason I know I need 4 equations is because I have 1, 2, 3, 4 variables that I'm looking for in order to come up with this. So for each variable we need to add another equation. So 4 variables, 4 equations. So 3 cubed plus 3 squared plus c times 3 plus d equals 22. And then 4 and then cubed plus b times 4 squared plus c times 4 plus d equals 21. Okay, so now let's go ahead and simplify these equations. Get a little bit more room. Okay, so simplified, these are what the equations will look like. A plus b plus c plus d equals 6. 8a plus 4b plus 2c plus d equals 15. 27a plus 9b plus 3c plus d equals 22, and 64a plus 16b plus 4c plus d equals 21. Now we would set these up as a matrix, and remembering that matrix, when we solve matrices, is AX equals B. So therefore, our matrix would look like this. This would be our coefficient matrix. So that's just going to be 1, 1, 1, 1, and then 8, 4, 2, 1. 27, 9, 3, 1, and 64, 16, 4, 1. And then matrix X, that's going to be what we're looking for, A, B, C, D equals B. In this case, that's going to be 6, 15, 22, and 21. And recall, we have to do, in order to solve that, is we have to get rid of the a by doing the inverse of a both sides, which would leave us with x equals the inverse of a times b. And we'll use our calculator for that. So here's my calculator. And I went ahead and already entered in all my matrices. So it's a 4 by 4, and I entered all those values here. And I also entered them into matrix B, the constants. So you can see those 6, 15, 22, and 21. So all I need to do now is go ahead and go under matrix, and I'm doing the inverse of A, and then times the inverse, or just times B. And there I have it. So there's my A, B, C, and D. Okay, so -1, 5, 1, and 1. So when I finally write my equation, it's going to be, so A is -1, so it's going to be -1 or just -x cubed. Okay, remember, now we're putting back our x's now that we found our A, B, C, and D. 5x squared, so I shouldn't be seeing A, B, C, or D in this final equation, plus x plus 1 equals y, or if you can flip it around, y equals this. And that's the equation that will give us a table, and you can verify that by entering this equation into your y equals part of your calculator, and then looking at the table, and you should get the same exact values. Okay. Our last example states the table shows the number of vehicles, y, in thousands, fueled by ethanol 85 each year, x, from 1999 to 2004. Want to find a polynomial model for the data. Use the model to predict the number of vehicles that will be fueled by ethanol 85 in 2005. So here's our table, where year 0 represents 1999. So this is the year since 1999. So 1990 itself would be 0 years away from 1999, and then all the way up to 2004. And these are the number of vehicles in thousands. Okay, that's important. I want to point that out. It's in thousands. Again, we're only given a table of values, and we don't know what type of equation or function we're going to use here. In using finite differences is not going to make a lot of sense, because A, these numbers are some crazy decimals, and B, it's real life numbers which don't usually fit those sort of models very well, because the numbers could be not exactly consistent. So we're going to utilize the help of our calculator, and we're going to do a regression. So I've gone ahead and entered in this data into my L1 and L2, x and y respectively, and I'm going to go ahead and go under Stat, Calc, and I'm going to start off with a linear regression and just see how that works. And I can see that my, now I'm primarily going to be looking at my r² value here for my correlation coefficient squared, and that's a 0.88, which is not a very good correlation for this data. So I'll try another one. So maybe it is quadratic, so I'll try quadratic regression, which is option 5. And I can see that that's a 0.96. That's a lot better. That's a much stronger correlation, but maybe we can do better still. So I'm going to go under Calc, and I'm going to do cubic, and that's a 0.986. That's a good regression there, and I'm pretty happy with that. So I'm going to go ahead and use that. This would be my values for A, B, C, and D, and I would record those. So my equations would look like this. And the next part is I want to predict using this model what it will be in 2005. So I can do a couple things. I could take 6 and substitute 6 in for x and find y. I went ahead and entered the equation into y equals here, using more values than I really need for carrying out to more decimals, but I like it really accurate like that. But you can just do it to the nearest hundredth. And I'll just utilize the table, and I can see that at 2005 that's going to be 6 on our table. It's 184.01. So therefore there were about, now remember that's in thousands, so I would write that as 1.84, so 184,000 vehicles. And that would be my solution. Okay, so that's the last section for Chapter 5, writing polynomial functions and models. Until next time, I'll see you on the flip side.